Hello, everybody, and welcome. This is your first lecture in Earth Science, so I'm so happy that you've joined me today. My name is Dr. Hurt, and we're going to be going over your very first subject, very first lecture number one. I hope you have your lecture assignment number one all ready to go. So, we're going to be talking today about a little bit strange subject. It's our only lecture that is not about science. Actually, today, I'm going to be talking about philosophy of science. And I started doing this lecture because I realized that going into this class, a lot of students didn't actually know exactly what science was. Some of them thought maybe science is everything, and maybe science can explore every subject, and et cetera, et cetera. But that's actually not true. And probably the goal today, pardon me, is to just delineate, make it clear, where does science begin and where do other subjects start? So that's our goal for today, and I hope you enjoy. We're going to get right into this. But first, I just wanted to give you, you all had a chance to kind of explain your bio and where you come from on the syllabus quiz, and I also wanted to do the same thing for you so that you kind of know a little bit about who you're dealing with. But just a little bit of background information. So I am a father of three children, three pretty small children, 7 years old. And, let me get my little pen out here. So 7 years old, there's Teresa, and 3 years old. Of course, these pictures are a little bit old now, so they look a little bit different now. And then I also have this guy, this is Frankie, so he was born just 2021, right? So not too long ago. I was born, actually, both my wife and I were born in Southern California. From Southern California, we're like one of those many Californians that have come to Texas. So, and it's for reasons like this. This is traffic on the 405, and that's what it's like. And there's a lot of people, and it's very expensive, and it's a little crazy in California. So we've left and come to Texas. But I got my bachelor's degree, my creds, right? Or I have a bachelor's degree in geology, and I have a PhD, master's. I have a PhD in earth and environmental science from the University of Michigan. So it's very, very cold there, and my wife was like, no, we got to move somewhere a little bit warmer. So I didn't mind it so much, but she really had a problem with the cold. So anyway, that's why we're here in Texas, and I love it, and I have no plans to move away. So I'll be here hopefully. This is the previous. Why did it go back? There we go. So anyway, that's me launching into the material. We start off with this very basic question of what is science? Well, one of the most important parts that you understand, kind of zooming out really far into, almost like metaphysics and what the universe is really about, right? You kind of have to zoom out that far to understand science. So we want to answer this question, what is science? Well, the first important thing that you understand about reality, about, the universe and nature is that it's intelligible, okay? So you've probably heard this word before, a cosmos. And I often ask my students, like, what do you think of when you hear the word cosmos? And most students will say the universe or outer space. Some of them say Carl Sagan, because he had that show, The Cosmos. But anyway, I had one student say she thinks of the drink Cosmos, like Cosmopolitans. That was kind of funny. But anyway, most of you probably think of outer space or something like that. Well, cosmos actually has a very specific meaning. The cosmos actually comes from a Greek word, and it means order or arrangement. Okay, and that's important because one of the great things about the universe is that there is order and arrangement. Okay, it's not just random jumble of facts or something, right? We are not a chaos. So the opposite of the word cosmos is another Greek word that you've probably heard of before, that's chaos. So chaos and cosmos are actually opposites. And chaos, you all know what chaos means, right? If you go into your room and you haven't cleaned it in a month, right? It's a chaos, okay? Everything's jumbled up everywhere and you can't make sense of anything. So we live in a cosmos, not a chaos. It means that the world is intelligible. We can make sense of it. So some of the results or the consequences of the fact that we live in a cosmos and not a chaos is that the natural world is ordered, it's rational, and it's intelligible. And that word intelligible, it comes from the same root as intelligence. So And intelligence is something that's able to make sense of what it sees and what it's exposed to. So our intelligence is able to make sense of the world because the world itself is intelligible. Okay? And it didn't have to be that way. We could have lived in an unintelligible world. A world where just strange, random, chaotic things happen, where there's no way to predict, there are no natural principles or something like that. That would be impossible to understand. But that's not the case. We live in an intelligible world. So because we live in an intelligible world, we live in a cosmos, it means that we're governed by natural laws. Okay, the laws of nature, like law of gravity, the laws of thermodynamics, etc. And so there are principles that are kind of undergird or support nature. Okay, and a lot of what science is about is just kind of discovering and understanding what those principles, what those laws are. This also means that nature is predictable, right? So think about how horrible it would be if nature wasn't predictable. Like, here's my cup of coffee. What if I took a sip of this and it turned into a dragon and flew away? Every time you did something random and strange would happen, right? But of course, we know that's not the case. I'm going to take a drink of this and hopefully it'll go okay. I think it went pretty well. So that's the beautiful thing about the world, right? It's predictable. And think about how strange it would be if it was not predictable. And it's predictable because it's governed by laws. It's governed by principles. It's governed by intelligibility. Okay? So, and all that means in the end that we can do science, right? We can do science. If there wasn't intelligibility to the world, if it was just chaos and randomness, we couldn't do science. Okay? So it's very, very, very important. Now, another question I have there on the lecture assignment that I don't have a slide to, but I want to discuss really quick is this kind of interesting word of science. What does it mean? So this word science, oh, by the way, I have no idea why this always happens. These little things go striking out like that, but I wish I could understand it. I've tried very hard to get that to stop, and it doesn't stop. But hey, this word science, it was kind of coined in the 12th century, 13th century by a medieval philosopher you might know named Thomas Aquinas. So Thomas Aquinas, there goes those little things striking out. Thomas Aquinas was writing in Latin at the time, and he has this term scientia. And you can maybe see the similarities between scientia and science. By the way, that term in like the lecture assignment, I said etymological roots. Etymological means like where the word comes from. Okay, so that's, if you ever hear that word etymology, it refers to where words come from. So scientia is tied to science. Okay, and what does scientia mean? Well, scientia is knowledge. And of course, there are a lot of different types of knowledge, and scientia to Thomas Aquinas was actually a very specific kind of knowledge. He actually divided knowledge into scientia and another thing called sapientia. Sapientia is maybe something like we would consider, the way that we would maybe translate that word, sapientia, is wisdom. Okay, so you can maybe think of people in your lives that are wise, or you consider them wise. You know that they have a certain kind of knowledge. Maybe it's a knowledge of like life and love and what's the meaning of life and things like that, right? And you could maybe see that that's one kind of knowledge, but another kind of knowledge is just like knowledge of technology and things and facts and science, right? So science is another kind of knowledge. It's a certain type of knowledge, and it's kind of like practical knowledge about the physical world, right? Not about kind of things, deeper things like wisdom, right? So I hope that gives you some kind of sense of what this word science means and what it refers to, okay, and kind of the history of that term. So there are a lot of different definitions of science. Here's one of them that I use. So science is a methodical reasoning, and I'm going to break this down kind of piece by piece, but it's a methodical reasoning that's ordered towards discovery of truth about the physical universe, and it's based on observation. Okay, so there's a lot of parts to that, and we're going to kind of unpack it and understand each part of it. So first of all, we say that science is focused on the natural physical world, okay? That's a really important aspect of science. And I think that's where a lot of confusion occurs with people in the modern day world. They think that science applies to everything and everywhere. Well, it doesn't. It doesn't apply to a lot of things. We're going to explore that later, kind of the limits of science and what science can do and what it can't do. But one of the things is that it's only limited to the physical world, okay? And when I say physical world, I'm talking about things that are like time, things that exist in time, space, and they consist of matter and energy. They have to exist in time and space, and they have to consist of matter and energy, okay? Atoms, things like that. That's what we can investigate with science, right? That's why we can't investigate things, for example, like I said, think of somebody in your life who's wise, who has wisdom, has sapientia, right? That's a different kind of knowledge. It's an important sort of knowledge, but it's a knowledge that does not have to do with atoms and energy, right? It has to do with love and life and the meaning of life and things like that. Okay? So what are some things you might look at that and be like, well, doesn't everything consist of time and space and matter and energy? And a lot of people think that, and they actually the answer is no. It doesn't, right? There are a lot of things that exist, they're real, but they don't exist in time and space and matter and energy. They're not physical. So a lot of examples of these things I have up here, just for example, mathematical truths, okay? Mathematical principles, I should say. So the fact that like 1 + 1 = 2, that's not based, we don't prove that 1 + 1 = 2. The truth isn't based on anything physical, okay? It's true, it's real, it's a fact of the universe, but it's not based on anything physical that we can touch. It's not based on matter or energy or time or space or anything else, okay? Another thing that's similar to that is logic, right? Logical truths are true whether or not there's time or space or matter or energy or anything else. They're always going to be true, right? So that's not based on it. Another thing that's kind of interesting is mind. Definitely we have a brain, and a brain is, of course, completely physical. It's made of atoms and matter, et cetera, et cetera. It exists in time and space. But we also have a mind, and the mind itself is not physical. So a lot of things that happen in the mind are not physical. That's, for example, why we have psychology, right, is a study of the mind. And it's different than, for example, something like psychiatry or neuroscience. That's more of the study of the brain and chemicals in the brain and physically how the brain works, okay? So there's mind and brain, and there, of course, there's obviously a relationship between them, but they're not the same. One is physical, one is not necessarily physical. Mind is not necessarily physical. So anyway, and also, a lot of people believe in a soul, right? Or maybe just vaguely that there's some part of human life that is not physical per se. So something different than just the body, and maybe that's the same thing as mind, but just different ideas for you to ponder about what could be real but not physical, if that makes sense. So in science, we're only interested in what is physical. That's all we can actually look at. Now, another thing you might notice, kind of again unpacking this definition of science, is that it's methodical. So you might know that what does it mean to be methodical? It means you follow a method. Well, what method is that? I'm sure you've heard by now in your college careers, your education so far, you've heard of the scientific method. So go over that one more time about what is the scientific method. Well, that's the method that we follow to do science, okay? So how does the scientific method go? Well, first of all, there's a lot of different ways you could break this up. I break it up into kind of 5 steps. But it's very important that you follow this method. I think that a lot of ways that people arrive at erroneous results in science is that they don't follow the method, they deviate from it. So the method is good, it's true, it's correct, and it's worked for us over the many centuries we've done science, so it's important to follow. But it starts with observing, right? Everything, like I said, in science is about observation. So you observe some aspect of nature, and it's kind of one of those things that makes you say, that's interesting, right? And you want to try to explain it and explain what you see. So, for example, you might observe something that a lot of people wonder about is like, why do leaves fall off the tree in winter? Or, why, I know that here in Corpus we don't really have like a lot of fall colors, or any fall colors perhaps, but you still might wonder, like, why do leaves fall off the trees during fall and winter, So the next step there is you propose some kind of explanation that you seek to explain that observation, that initial observation that made you say, that's interesting, right? And that next step is called a hypothesis, so a hypothetical statement. So a hypothesis proposes an explanation that seeks to explain that initial observation, okay? So what are some hypotheses? Like, I could even ask you, what are some hypotheses that you could come up with to explain why leaves fall off the trees in the fall, okay, or in the winter? So if you think about that, you might come up with a few things. One thing that almost everybody thinks of right away is that it gets cold, right? So it gets cold in the winter, and that's what maybe causes the leaves to fall off the tree. Now, there's an important thing I wanted to point out here, is that I just said the word cause, right? So it's the cold that causes the leaves to fall off the trees. Well, a lot of hypothetical statements, that is hypotheses, are causal. That means they propose some kind of a cause and effect. Okay, that's what it means to be causal. You're proposing a cause and effect. Okay, it gets cold, makes the leaves fall off the trees because it gets cold, right? So that's hypothesis number one. Now on the test, I often ask you to kind of take a list of statements and pick out the ones, or the one that is hypothetical. That's a hypothesis. And what you're looking for in that is a cause and effect statement. Now, here's another hypothesis that people don't always think of right away, is that maybe it's actually getting, the trees are actually reacting to shorter daytime hours, right? Because you know that in the fall, in the winter, the days are changing, right? The length of days are changing. So days get shorter throughout the fall, for example. But in any case, you're going to adopt one or more of those hypotheses, and then you're going to make a prediction that seeks to prove or disprove that hypothesis or hypotheses. So, number one, a lot of people get confused about what is a hypothesis and what is a prediction, okay? But a prediction is based off a hypothesis. It's based off a hypothesis. So we're going to make a prediction. For example, if trees lose their leaves in the fall because it gets cold, that's my hypothesis, then a tree kept in a warm greenhouse over the winter will not lose its leaves. Okay? So a prediction is just what it sounds like. It's an expectation of an observation that we might make in the future if hypothesis 1 or hypothesis 2 is true. Okay? We expect to see this if my hypothesis is true. Okay? So it depends on the hypothesis. Now, our final step is we're going to test the prediction. So our prediction is that if we put that tree in a greenhouse and keep the temperature level, not abnormally, but artificially warm, okay, then the leaves should not fall off the tree, because that's what's causing the leaves to fall off the tree, is the temperature change. Okay, so we actually do the experiment. We put the plants inside of a greenhouse over the winter and we see what happens, right? Now, after that, we just have to analyze our results, okay? But you notice that all an experiment is an observation. All a prediction is an expectation about an observation we might make, right? So again, everything's kind of tied into observation, observation, observation. This word, observation, it's tied to another word that I ask about in the lecture assignments called empirical. Okay, empirical. And I think I do ask about that in the lecture assignment. So what does empirical mean? Again, it just means based off observation. Okay, So science is about observation, observation, observation. Now, one thing I wanted to kind of make a distinction between, because again, it's something I ask about on the test, I want to make sure you get this right on the test, is that a hypothesis and a prediction, what's the difference? Okay, because a lot of people I notice confuse the two. And I even noticed this in grade school, like the way my kids learn, in school, they're being taught that a prediction is a hypothesis, prediction. They're getting the two things confused. So a hypothesis, again, is a proposed explanation. It hasn't been backed up with a lot of evidence yet. It has not been backed up with a lot of evidence. It's just a proposed explanation. It's kind of a guess at why something happens. X happens because of Y, okay? It's causal. It's saying this happens because of Y, or this happens because of X, okay? Now, a prediction's different. A prediction is based off of what we expect to see. That's all right? I mean, you know what a prediction is, right? But so many people get that confused with a hypothesis. So, for example, I'll hear a lot of people say this. Now, this is incorrect. I'll hear a lot of people say, like, what's your hypothesis about what will happen? Well, that's not a hypothesis. That's a prediction. What's your prediction about what will happen? Okay. So, if the leaves fall off the trees in the winter because it gets cold, then the tree stored in a garden during the winter should retain its leaf. That's a prediction. Okay. It's a prediction that should be true if the hypothesis is true. So look for, when identifying a hypothesis, look for those causal statements. That's what's going to help you to identify the hypothesis. Okay. So I need another drink of coffee because my throat's getting kind of dry. All right, now that's sort of like the unpacking of that definition of what is science. Okay. However, there are some other aspects of science that, again, this is going to delineate. It's going to make limits and lines and boundaries about what is science and what can be answered by science and what cannot be answered by science. So what is in the science box and what is outside the science box? Okay, that's what we want to determine. Because I think a lot of people today, they are very impressed with what science has done and what it's capable of, and it's done a lot of amazing things, but they go too far. Okay, and I see this a lot with students. They go too far. Science can't do everything. It can't answer every question, but it can answer a lot, but it can't answer everything. So I want to say, where are the limits, right? Where are the limits? Where are the boundaries that determine what it can answer, what's science, what is not? So these are the three things I'm going to talk about right now. So science has to be observable, okay, and that means based in the physical observation. So it's based on evidence, right? So evidence is just observations, again, observations of the physical world, okay? It's got to be falsifiable, and I'll explain what that means later. I know it's a weird word right now, but it has to be falsifiable and it has to be reproducible. So let me unpack again what each of these statements means, okay? So first of all, observable. Science, again, it's empirical, right? Science is empirical, and that just simply means that it's based off of observations. Observation, observation, observation. I keep saying it. Okay, so we have two kinds of observations. We have qualitative and quantitative. Qualitative and quantitative. So what do those two things mean? Well, qualitative observations are ones that are focused on qualities. Qualities. So those are things like color, shape, form. They're observations of the physical world that can't be measured. Okay, so it's kind of hard to measure a color, for example. It's maybe kind of hard to measure a shape exactly, like especially like, for example, like you're kind of describing the shape of an organism or something. You know, it's hard to quantifiably measure that exactly. So we express it in terms of just qualities. Okay. That's one kind of observation, but we highly prefer in science this other type called quantitative. Quantitative is where we measure quantities and we make very precise observations that way. So, for example, this weather station is measuring out all these different quantities like wind speed, right? Temperature, barometric pressure, things like that. Okay. Whereas this paleontologist right here is maybe describing the shape of what I can't really tell if there's a he or she, but the shape of what they're looking at. Okay. Now, Here's a question for you that I think is just kind of fascinating. I want to share it with you, and I do ask about this in the lecture assignment. But what are some properties of the physical world that we can measure? So if you think about that for a few seconds, what are some things in the world that we can measure? Okay. So obviously I can't hear your responses, but a lot of things people say is, well, we can measure things like time. Yeah, and distances, and maybe like weight or mass. Okay, that's the one I commonly hear. And some other people, now I'm going to make another column over here. So here's column A, whoops, and there's column B, okay? And I'm going to make another column here because some people will say something like speed, and some people say things like volume, like, liters or gallons or something like that. And I put those in a separate column. And another thing I hear a lot of people say is temperature. Okay, I'm going to put that in column A. And I'm going to explain why I put some in column A and some in column B. So what it turns out is that these are all good things that a lot of students mention in class. What it turns out, though, is that there's actually only 7 distinct, independent, measurable quantities in the universe. We call those dimensions. Okay, so there's only 7. Now, I know that when you hear the dimension, you usually think of like 3 dimensions, right? You can move this way or that way or to the side, right? 3 dimensions. And I don't mean dimension in that way. We mean it in a different sense of things that are measurable, extents that are measurable. So I know that's a weird term that you probably haven't heard dimension used that way before, but that's what I mean here. So it's a different, there's actually only 7, I'm going to put my pen down, 7 different dimensions to the universe, 7 different things that can be measured independently. So in column A, these are things that can be measured independently. These are things that are dependent. And what do I mean by dependent? Well, I'm going to explain that in a little bit. So I got to erase all the ink on the slide so you can see this. Okay, but these are the 7 that are independent. That means they don't depend on anything. And they are distance. We already mentioned these, right? Distance, time, mass, temperature. And there are 3 that kind of people usually don't think of. Electrical charge, amount of a substance, and luminosity. Luminosity and electrical charge and amount of substance we don't even talk about in this class. But we do talk about distance, time, mass, and temperature quite a bit. Okay, but anyway, what does it mean that things are independent or dependent dimensions? So, there's a lot of other things that we can measure. For example, we can measure speed, we can measure force, we can measure accelerations, we can measure, there's all sorts of things. Density, we can measure volumes, surface areas, right? We can measure all sorts of things. So, those are all, however, dependent on the independent variable. So what does that mean that they are dependent or independent? So let me show you. Consider density. Density is defined as the mass over the volume, right? So volume, if you think about it, is just a distance by a distance by a distance. Okay, it's just 3 distances linked together. Mass is, like I said, a mass. So if you think about this, density is not an independent thing to measure in and of itself. It is based on mass and 3 distances. Okay, so it just breaks down into some combination of those 7 independent variables. So I just think that's fascinating that the universe, there's only 7 independent things that can be measured. Everything else, it just breaks down into some combination of those 7. So just a little kind of interesting thing that you might not have known about the universe. So anyway, that's measurement, observation. It's got to be physical observation. Okay, that's what science is based on. That's what we can do with science. Now, the next thing is a really strange idea. Probably a lot of you have never heard of this before, and that's okay. I wouldn't expect you to, but it's called falsifiability. Another term for this is verifiability. And let me try to explain what falsifiability and verifiability mean. Falsifiability, there's several terms for this. You could call it falsifiability, verifiability, or refutability. It simply means that a scientific claim or a hypothesis or whatever we're interested in, some kind of subject of inquiry, some kind of question that we're asking, in order for it to be science and to count as science, it has to be you have to be able to prove it true or prove it false with evidence theoretically. Okay? So here's another definition. This is just from Wikipedia, which is not always great for everything, but for this case, it seemed pretty good definition, so I took it. But it's the capacity for a statement, theory, or hypothesis, scientific, to be contradicted by evidence. Evidence, remember, what is evidence? It's observation. Observation of the physical world. Okay? So, for example, all swans are white. Is that a scientific question? Yeah, it is, because you could prove it's true or prove it's false with an observation. Now, it happens to be that this statement is false. It happens to be this statement is false because there are actually black swans, by the way. They're black swans in Australia, right? But it's a statement that you can prove true or prove false with an observation in theory. Okay? So that's what it means to be falsifiable or verifiable. Okay? What are some examples of things that are not falsifiable? So let me give you an example, something that is not falsifiable. Let's say that a scientist, kind of a zany scientist, wanted to look into a hypothesis he had that, bachelors are generally unmarried. And he wanted to do a study to see if bachelors are married or unmarried. Well, that would be silly, right? There's no point to doing that because we know by definition that bachelors are unmarried. That's part of what it means to be a bachelor, okay? So when we're investigating things such as meanings of words, okay, meanings of words, those are not falsifiable or verifiable by evidence. They're not falsifiable or verifiable by evidence, okay? So that's what makes it that's what makes it either science or not science. Okay. So I hope that makes sense. Now there's lots of examples that we can go into, and this is a very subtle idea. Okay, so I hope if you're listening, it's really important to pay attention because I do ask about this, right? On the lecture assignment, one of the questions I ask is come up with a question that is not answerable by science. Okay, so listen carefully now. I'm only writing this up there because a lot of people just skim through this on YouTube. So I'm just writing. Listen carefully right now because I'm going to try to answer these things. Okay. So what are some examples of questions that could be answered by science? They're verifiable or falsifiable. Okay. Now one thing that can't be answered by science, like I said, is the meanings of words. Because we cannot verify with evidence that, what the meaning of the word bachelor is. Right. However, we can verify with evidence. We can answer the question, are all swans white? Because we can go out and observe that there are black swans or there are white swans or whatever. We can go out and look at that. Okay, so I just want to talk about some ways that students go wrong on these couple questions that I ask. And I'm going to get out the lecture assignment packet so I can remind myself what questions these are, right? But I think these are the ones. I think it should be number 6 or 7 on your lecture assignment packet if you have the same version. So, I want you to come up with a question that is not answerable by science. Okay? So I want to just explain some things where people go wrong with this. Okay, number 1, we're talking about ignore technological limitations. Ignore technological limitations. So, for example, I've had some students get this wrong because they'll say, here's one I hear a lot. Do aliens exist? Well, we can't answer that with science because we don't have the technology to go out and explore the whole universe. So, yeah, that's true. However, that's a technological limitation. I'm talking about theoretical limitations, okay? So beware technological versus theoretical. I'm sorry for all these annoying little things that come. I don't know why that happens. So technological versus theoretical. Ignore technological limitations. We're not interested in that. We're talking about what is possible in theory, okay? So aliens, do aliens exist? That's a scientific question because we can go out and verify with an observation with our eyes and see if they exist or not in theory. Maybe we don't have the technology to do that right now, but we might in the future, okay? So ignore technological limitations. Another thing is that a lot of times people just get this idea of false versus falsifiable. I've heard this example before. Hey, how about this for a question that is not verifiable or falsifiable? The sky is blue. The sky is blue, so it can't be proven false, so it must not be falsifiable. Okay, that's totally wrong, right? Because they're getting the word false and falsifiable confused, okay? There's a difference between false and falsifiable. Falsifiable means that something can be theoretically proven false by evidence, okay? So whether or not that evidence has actually been collected yet due to a technological limitation is another question, but it can theoretically be answered by a scientific observation. So here are some good examples of things that cannot be answered by science. Mathematical principles, okay? Mathematical principles. So proving that 1 + 1 = 2 or 2 × 2 = 4 or whatever, that's a good example of something that's not falsifiable because it's not science, because mathematical truths cannot be falsified by evidence. Here's an example. Let's say you take 1 cup of water and 1 cup of sugar and you mix them together. How many cups will you get? Will you get 2 cups? 1 cup of sugar plus 2 cups of water? 1 cup of sugar plus 1 cup of water. Will you get 2 cups of sugar water? No, you'll get something else. Because the sugar is going to dissolve into the water. Have I therefore proven that 1 + 1 does not equal 2? Of course not, right? Because mathematical truths don't depend on physical observations, okay? We use mathematical principles to explain physical phenomena, not the other way around. So math is sort of above science in the world, right? The world and the physical world does not prove math. Rather, the math can be applied to explain phenomena we see in the physical world. Okay. The last thing here now, I don't want to beat a dead horse, so hopefully that some of that stuff made sense to you. But the bottom line is here with falsifiability, you have to be able to theoretically, don't forget that word theoretically, you have to be able to theoretically prove something true or false with evidence. Okay? That's what makes it falsifiable or verifiable. The last thing is reproducibility. Reproducibility means that other people have to be able to come and make the same observations that you did, do the same experiments, and get the same results. Okay? So this is why, for example, we don't study in science like your feelings or your emotions. I mean, we can study emotions generally, sort of, in the brain, maybe like hooking up electrodes to your brain and looking at which parts of your brain light up when you feel different emotions. But that doesn't tell you how you actually feel when you're angry, or how you actually feel when you're in love, or how you actually feel when you're afraid, right? Because we can't really study emotions and things like this, because for one thing, they're in the mind, and another thing is that they are totally subjective and depend on you, and nobody else can go inside of you and experience what you experience. So they have to be reproducible. Other people have to come and be able to make the same observations that you make. Okay? So just to put it all down here, these are the 3 things that have to be true in order for something to be a valid scientific question. It has to be based on observation of the physical world. It has to be possible to prove it true by observation, or prove it false by observation of the physical world. That's falsifiability. And again, the important word there is theoretically can be proven true or false by observations of the physical world. And that evidence has to be able to be reproduced, or it's visible and can be viewed by everybody and experienced by everybody. Okay, so that's reproducibility. Some examples, and I'll end here I'll end here with what is science. and go a little bit into what's earth science. But what are some science questions? What are some non-scientific questions? So a science question is, what parts of the brain are active when someone's in love? We can hook electrodes up to your brain and look at brain activity when somebody like you're in love with walks into the room, and we can see like what happens to your brain. Okay, so that's science, right? That we can observe that. We can observe. Everybody can see the evidence. Blah 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 blah. Okay, what's not science? If I ask the question, what is love? Very important question, but totally invisible to science. You can't answer what is love with science because it's a definition. It's a meaning of a word. Science can't give you meaning. It can't give you meaning of anything. It can just tell you about observations. Okay. What's the average discharge of the Delaware River? Okay, that's a science question, right? We can observe and measure how much water actually is discharged from the Delaware River per year. Okay, we can't do something like history, because nobody can reproduce historical occurrences. So that's why we have a whole separate field of study called history, where we study single historical events. We don't study that with science, right? You don't take a science class to learn what happened. Did Washington cross the Delaware? What year did he cross the Delaware, right? You don't do that in a science class. You do that in a history class. Why? Because they're single, unreproducible historical events. Okay. What's the surface area of the Earth? We can measure that, right, with science. However, what does 1 + 1 equal? That doesn't depend on the physical world or anything about the physical world, okay? That's a mathematical principle that's verified through logic and mathematical proofs, not by scientific observations. All right, so that's science. So I hope now that you have a little bit more understanding of what science can answer and what it cannot answer, okay? So now that we've done that, I want to just kind of briefly go into a little bit about what is earth science, okay? So earth science is an umbrella term. That means that it involves a lot of different things. And I mean, it's all the different sciences that come into the study of the earth. So it includes a lot of geology. Probably about half the class is geology, maybe a little less. And that's the study of rocks and minerals and the surface of the earth and all the way down the mantle and the core and the kind of rocky, hard parts of the earth is maybe what geology encompasses. There's environmental sciences, right? That's where we study environments. We study especially like natural waters, streams, river. You can see these young ladies here, maybe taking measurements about a creek. A lot of it, environmental science is focused on water because a lot of pollutants and things like this are transmitted through water, right? We study oceanography. We're going to spend a week on oceanography here. And by the way, if you like it, I have a whole oceanography class that students usually like too. So we do that. We do that in earth science as well. Okay, and we also do meteorology and study of climate. And actually, even beyond that, we also study the night sky and things like that. So you're going to learn really every scientific aspect of the earth, right? We look at it a little bit in this class. Now, why do we study? What are the societal benefits of the study of earth science? Well, there are 3 of them that I mentioned here, and there, of course, there are more. But one of those is natural resources, right? So we provide natural resources to the world, okay? If you look around you right now, almost everything around you had to be discovered. The natural raw materials had to be discovered by an earth scientist. So aluminum, metals, iron, plastics. Guess what? A lot of your plastics, guess where they come from? Petroleum byproducts, right? So petroleum has to be discovered by geologists. Aluminum comes from a mineral called bauxite, has to be discovered by biologists, or geologists, sorry. Copper, right, in all of your electrical devices has to be discovered by geologists, right? Aluminum, copper, iron, steel, we use all these things. They have to be discovered by geologists. If you look at your smartphone, a lot of you have a smartphone, right? Not everybody has a smartphone. Well, guess what? Your smartphone has all of these elements in them. Isn't that crazy? Things that you probably never even heard of before. Yttrium, praseodymium, europium, lanthanum, terbium. Have you ever heard of these? But there are all these elements that are in your smartphone. Guess what? Geologists have to discover where all these elements are so that they can be mined so they can go into your device. So It's not necessarily a pretty thing, but it is something that we use and we depend on in the modern world. Okay, so anyway, geologists are there, earth scientists are there, discovering all these elements to help you. So that's natural resources, right? Now, on the flip side of things, we're looking for natural resources to use, but we also usually degrade the environment when we mine or harvest those things. So on the flip side, earth scientists are also repairing the damage that they're doing by taking advantage of the natural resources. So we study all sorts of things in the environment, right? So the bleaching and I just put some things here, some examples of like environmental problems that we might be interested in studying as earth scientists. Bleaching of the Great Barrier Reef, that's something earth scientists study. Melting in Greenland, in the Greenland ice sheets. Algal blooms. Maybe you've heard of like algal blooms here in Corpus Christi. Sometimes there's red tides and there's harmful algal blooms, right? Those are all things that earth scientists study. Yucca Mountain radioactive waste station. 19% of our energy here in the United States comes from nuclear, right? So nuclear power. Where does all that spent uranium go? That spent uranium fuel. It's highly radioactive and dangerous. Well, it goes into Yucca Mountain, this radioactive storage facility, right? And we all just kind of hope that groundwater and other things don't carry those radioactive isotopes away and transmit them and spread all throughout we can keep it isolated there. And that's a big deal. A lot of people work on that problem of how to keep us safe from these spent, like how do we store spent radioactive waste? Big problem. And we need people. So, it's something, if you're interested in the environment, you might want to become an earth scientist and help work on some of these problems that are going to be plaguing us in the future, right? And natural resources, all these things are gonna be major issues in the future. So it's something we need people to study. So another place where earth scientists benefit society is through natural hazards and mitigation of natural hazards. Tsunamis, volcanoes, earthquakes, all these things. I could go on, right? Here, hurricanes are a problem. Okay, there's all sorts of things that. Wow, earth scientists have helped so much. 2004, probably you are all too young to remember, probably a lot of you are too young to remember the 2004 tsunami in Indonesia, but it killed 190,000 people. 190,000. Think about that. How many people died in 9/11, right? 3,000 or so, right? Think about if we were to lose 190,000 Americans, right? Or I guess I could bring up the coronavirus, things like that, right? That is something on the same order of magnitude. So you could see that, these are big deals, right? And in Japan, you might remember 2011 Japanese tsunami only killed 10,000 people. The tsunami. Why did Indonesia killed 190,000? Japan, they only lost 10,000 when it's a much more dense, population density is much higher in Japan. It was because of the warning systems that had been installed by seismologists and others, earth scientists, that were able to give people a warning to get to high ground to avoid that tsunami. Okay, so we could have lost millions of people in Japan because of this, but it ended up just being 10,000, which is a tragedy, but it's a lot better than it could have been. So, you save lives, you save the environment, and you provide natural resources that people depend on for the world. So it's a great field to study, and I hope you enjoy this class. I'm going to stop here now, but I hope you enjoy this class. You understand how important it is, and also, how we could possibly help as earth scientists in the future. So I'm going to stop here, and I hope that you have a nice week. And just let me know, I'm here to help you, so please let me know if you have any questions or concerns. I'm here to serve and help you along your way in this class. So please don't be afraid to reach out. So I'll see you next week or talk to you next week through this lecture. So thank you for listening.